Welcome to Ladder Logic. I want to do a series of videos on ladder logic, more specifically about pneumatic ladder logic or electro-pneumatics, to kind of bring you up to speed. So we're going to do kind of one step at a time. So this is our first video on electro-pneumatics, ladder logic. What I want to focus on is kind of the difference between a double-acting solenoid valve and how that looks in ladder logic, and a single-acting solenoid valve and how that looks on ladder logic. You know, depending on actually whatever we want those things to do, whatever we want that solenoid valve to make the cylinder do, our circuit's going to be different. Because one of those valves has a solenoid and a spring, and the other just has two solenoids. So I need you to kind of just understand a concept here, and I'm going to draw a couple valves. So what we've got here is we've got two cylinders, A and B, both being run by different DCVs. So this DCV is still a 5-port 2 position, this DCV is still a 5-port 2 position, but the activations of the DCVs are a little bit different. So over here, my 1-2 activation from here to there is done by the spring. So when this is not active, when this solenoid is not active, this cylinder will actually return. So if I do not activate that, that cylinder will return. The reason is because the spring moves and turns this into a 1-2 state. Okay, over here it's different. Over here I've got two solenoids. So this is going to be solenoid A plus, it's a capital, and that's A minus. Over here, this is solenoid B, not very good, B plus, B plus, and this guy is just a spring. So over here, the actions are different. If I don't activate that and I don't activate that, we actually don't know where this cylinder is. I mean, if I were to have activated this and then turn it off, this would stay out. So if I activated this, the cylinder would extend. I think we're good with that. But when it does extend, if I deactivate this, does the cylinder return? Well, no, because the air here is still 1-4. So that's 2 and that's 4, and we know that, and that's 1. So when I activate this, my air goes from 1 to 4 and this goes out. When I deactivate this, the valve doesn't move. It doesn't change. And it's really important that you get what I just said, that this acts completely different from this, because when I de-energize this, that cylinder, it doesn't move. Okay, over here, when I de-energize this, this cylinder moves. It returns. The reason it returns is because this valve has a normal state. So the valve actually goes into a 1-2 state. So in that the air from here 1 goes to port 2. And soon as I de-energize this, this cylinder will retract. Okay, so let's just say I had one button. And if I press that button, my cylinder will extend and just stay that way. Over here, it's super simple. Watch this. Okay, my cylinder is going to extend. Now, I want to do event programming. I want to just completely focus on event programming. Okay, so that's 0 volts, and this guy is 24 volts. Over here, I'm going to put a normally open push button there. The event that makes this cylinder extend is that somebody pressed the button. If I ask you what an event is, if you start talking about limit switches and contacts being open and closed and normal states, and I get a little upset about you. I get a little upset about it. So just chill. An event is something that happens. It's not electrical. It's an actual event. The temperature goes up. The level goes down. Somebody pressed the button. Someone opened the door. Something like that. There's a fire. Okay, here we go. So in this case, the event that makes this go out is someone pressed the start button. Okay, I'll make this start. Okay, good. So press it and that goes out. Now I have to label this solenoid A. Now I don't have to label it. I can label it A plus in this case. Absolutely, I actually have to label it A plus because in this case there are going to be two solenoids. So if I wanted this to retract, well, it would depend on what event I wanted to have to make it retract. I'm not going to put that in yet. Over here, we're going to do the same thing. Now, the control discussion is that if someone presses the start button, the cylinder goes out and it just stays out. Okay, let's take a look. Did we do that here? If I press this, that energizes, it energizes this, it moves the spool in here. Now I've got a 1-4 valve, and it stays as a 1-4, so the cylinder extends and stays extended. Let's do the same thing over here. Okay, so I've got my ladder logic here, 24 volts, and down here I've got my start button. I'm just going to go in a little further for my start button. Okay, so there's my start button, and here's my solenoid. Now this is solenoid B+. Okay, good. So let's see what happens here. I press that button. The event is that somebody pressed the button. Okay, so if they press the button, absolutely, this will energize, the spool will move, this becomes a 1-4 action, so now my air is coming out here and it makes my cylinder extend. Sweet, okay, my cylinder extended. Now I let go of the button. That's the problem. As soon as you let go of the button, that de-energizes, the spring takes over, and the cylinder comes back. Over here, it doesn't happen. If I press this button, that energizes, this becomes a 1-4 valve, and then when I let go of this, it stays a 1-4. In this case, as soon as I let go of this goes into a 1-2 state. It absolutely will retract this cylinder. So, well, what do? Let's put a holding circuit. So, put a holding circuit? Okay, good. We know a holding circuit looks like this. You have to put, and I'm going to put R1-1. Okay, so we know that my holding circuit has to go around the signal that I'm trying to hold. Well, what signal am I trying to hold? Well, I'm trying to hold the event that someone pressed the button. And we know that that event is translated into an electrical impulse with a switch or a sensor. In this case, it's just a normally open push button switch. I'm going to label it start. So in this case, when I hit start, the cylinder will go out and stay out. Is there anything missing here? Well, yeah, the relay coil. Okay, so I'll put that in here. I'm going to put now, you know, the relay coil, I'm going to call that R1. Absolutely, you know this, that a relay coil that is associated with a holding circuit has to be driving the holding circuit that it's associated with. Does that make sense? I can't use an R2 if there was one down here. I absolutely have to be driving the coil that the contact is associated with. So, but you guys know that. Okay, good. So, as far as electro-pneumatics goes, we just designed our first circuit. You press play, it goes out, and it stays out. All right, let's add some logic. What event is going to make it retract? Well, I think we can go with a real simple one here, and that the event that's going to make this retract is that it's extended. So the event is, to make it start, is that someone pressed the start button. The event to make it retract is that it extended. When you really think about event programming, I don't want you guys thinking, well, the event that makes it come back is the outside limit switch becoming closed. No, dude. The event is that it extended. Okay, so how do we translate that event into an electrical impulse? Well, through a switch or a sensor. Well, in this case, we're going to use the outside limit switch. Now, it's normally open, which I didn't draw before. Okay, good. So that's normally open. These guys are normally open. So let's put that in there. And I think you've probably noticed that there's no termination contact on this holding circuit, which is a real problem, but that's okay. We have one now. Okay, so I'm going to draw this first, and I'm going to stick that onto a relay. And I'm going to call that my R2 for sure. Now, why am I using a relay? Why don't I just put the limit switch here? Well, the problem is the limit switch is a normally open. If I put a normally open limit switch there, this would never happen. So I can't put a normally open limit switch there. I have to put a contact there that's normally closed. And that's because, well, really just it boils down to our termination contact, 99% of the time, is normally closed. Okay, so what I'm going to do here is I'm going to think about my limit switch. Now my limit switch is going to be a normally open because it says so. So it's a normally open held open. It's held in its normal state. So I'm going to do this guy and that guy, and I'm just going to label this here, normally open, held open. Now, you don't actually have to label that in your drawing. I'm going to call this LSB+. You don't have to call it normally open, held open, but I mean, it's good practice maybe as you're starting, your brain kind of getting a hold on the terminology, but really it's about how you draw it. That's the most important part. Okay, so now let's see if this works. I have to put a contact here over here, okay, and I know it's going to be normally closed, okay, so that's my R2-1. If I press play, there will be power here, there will be potential voltage here because that guy's in its closed state, because that guy's in its normal state, because it's open, And this is open, so therefore that's de-energized and that's in its normal state. Right, okay. So now I got power here, I press play, that energizes, this actually moves the spool, this energizes, this becomes closed. When I put my finger off of that, take my finger off of that, then this actually stays energized because of my holding circuit. And when it goes out, so you know what? The reason we need this holding circuit is because if I let go of the button while the cylinder, say, gets here, it's moved this much. It hasn't gone the whole cycle. And I let go of it, it'll come back. So the function of this is that it has to go all the way out and then come back. So we can ensure that it does go all the way out with this holding circuit, although I could hold the button a little longer until it got out and then just release it. That would be nice and simple, but we want this automatic. Okay, good. So this guy now becomes closed when the cylinder goes out. That energizes, this goes into its active state, which is then open, and it terminates the holding circuit. As soon as we terminate the holding circuit, as long as my finger's off the push button, then that guy's going to de-energize, so will that guy. This guy will become open, this guy will shut off, and the spring will take over and return the cylinder. So over here, we have something that's really simple. It's like this. Now, if you notice this, over here, we've only got one solenoid. We can do two things with it. Well, it's because if we turn it on, it does something. If we turn it off, it does something else. In this case, if we turn that off, well, nothing happens. So I have to actually put this guy into my circuit. Okay, I'm going to put this guy in my circuit over here, and that's going to be solenoid A minus. So if that makes this happen, that's this guy here. And what do I put here? You know what I'm going to put there, but I still need to reiterate. We're doing event programming. What event makes it retract? Well, the event is that it extended. Okay? Okay. So what is the electrical impulse that I'm getting? What thing gives me that electrical impulse? Well, a limit switch. It's the outside limit switch. So I'm going to take this guy. In this case, it is I'm not going to label it. It's a normally open, held open switch. And this, I'm going to label it here. This is limit switch A plus. Okay, so that's actually the first part of lab 1. But I needed you to understand why. So I think you get that. So what we've learned here is that with this guy, if we want that to stay out because of a momentary push button, we have to have a holding circuit. Over here, if we want this to stay out, we don't need that holding circuit, but we do need two solenoids. Cool, so we're done for this one. The next thing we're going to do is we're going to add a little bit more logic to this and kind of discover how we can deal with the fact that this guy is held closed and this guy is held closed. So let's put that into the ladder logic.